So I am doing some work on CO2 outgassing in the subpolar North Atlantic, and this is work that I have been studying with Sarah Perkey and Fiamma Stranio on as part of my PhD here at Scripps. So this is a bit of a diversion from my own field of physical oceanography and kind of what OSNAP mostly focuses on. So I just wanted to touch on some kind of carbon points here. The ocean absorbs 25% of the excess CO2 that human activity has put in our atmosphere, and the North Atlantic has the highest column inventory of anthropogenic carbon. So you can see up here, the subpolar North Atlantic region where that deep water formation and overturning happens has a really high column inventory of anthropogenic carbon. And then if we think about exchange with the atmosphere, the subpolar North Atlantic is one of the most intense sinks for atmospheric carbon, as shown in this Landshutzer climatology, which is a data product, a gridded data product. So if we zoom in to that Landshutzer climatology around focusing on the subpolar North Atlantic region, we see that the annual CO2 flux into the Erminger Sea, sorry, I should have said blue is into the ocean for the flux here, and red was out. So the annual CO2 flux in the Erminger Sea is much weaker, kind of around zero annually compared to the rest of the subpolar North Atlantic region. And so kind of reasons for why is what I've been trying to explore and untangle. So if you're not familiar with what governs CO2 flux, it's driven by the gas transfer velocity, which goes like the square of the wind speed, the solubility, and then the difference in the partial pressure of CO2 between the ocean and the atmosphere. So if we break down that annual mean CO2 flux climatology from Landshutzer, I've just made a monthly climatology just using the just over the 2004 to 2016 time period, and plotted maps for 1 month per quarter. And you can see that in the winter, there's actually a significant area of outgassing in the Erminger Sea, which you don't see on the Labrador Sea side or kind of around to the north and south. And that then decays off as summer progresses into spring, as winter progresses into spring, and in the summertime, the whole region is back to being a CO2 sink. So this gives us an idea as to why the annual mean CO2 flux is weaker. Sorry about the sound. There's nothing going on in the background. Is that just me? Or others having trouble hearing?
It just sounds like some background noise, Monica, maybe. Now it's partially gone. Yeah. But I think we can still hear you though, so.
Okay.
Yeah.
Okay. Sorry about that. There is a plane flying overhead, but okay, so that kind of leads to the question of, okay, so what is different in the winter in the Labrador Sea compared to the Erminger Sea? In terms of what's going on in the Erminger Sea, work has been done to see that the sea surface PCO2 is related to mixed layer depths, so that when the mixed layer begins to deepen, the sea surface PCO2 dramatically increases, and then that tails off as the mixed layer continues to deepen. And this is attributed to the fact that there is entrainment of DIC-rich waters from below when you deepen the mixed layer. So this plot shows kind of a typical DIC profile in the ocean where the DIC is depleted near the surface from biological activity, and then increases with depth as remineralization occurs. So as you deepen the mixed layer, you can sort of punch into these more carbon-rich waters and bring it up to the surface. But that doesn't explain why we don't see this in the Labrador Sea. In the Labrador Sea, the mixed layers are just as deep and normally deeper in the Labrador Sea than in the Erminger Sea. So given that the Labrador Sea is a more prominent region of deep convection, why don't we see that same wintertime outgassing of CO2 on that western side? And this is kind of where I had been stuck at for a little while, but I recently read a paper that just came out earlier this month by Olsen and others, looking at the eastern side to see how annual, kind of what the seasonal cycle of the CO2 flux is in various basins that they segment off. So the Atlantic region, the Arctic region, and the polar region. And they see CO2 outgassing only in the Atlantic waters of the Erminger Sea and not in the Arctic or polar waters. And so what they attribute this to is the fact that the Arctic and polar waters have more freshwater input that has come from terrestrial sources carrying higher alkalinity, and that higher alkalinity actually suppresses the sea surface PCO2. So if you bring down the sea surface PCO2, then you have the ability to kind of maintain that year-round carbon sink in terms of exchange with the atmosphere. So what I'm now thinking is, can we sort of extend this to the Labrador Sea side? Is there, if polar waters have higher alkalinity, which are lowering the sea surface PCO2, is there more opportunities for that water to get into the Labrador Gyre and kind of exchange off the shelf where it is mostly confined, shown in green here, and therefore can that explain what is going on in the Labrador Sea and where we're not seeing the wintertime outgassing? And I'm kind of looking forward to kind of hearing a bit more and seeing where, I know several of you are sort of looking at this exchange, where freshwater is going in exchange with the shelf. So it would be interesting to kind of keep in touch with you guys about that. So I started to look just at a couple of Argo floats. As I mentioned, I kind of just came across this paper and idea about a week ago. So very fresh with this, but looking at some BGC Argo floats, one in the Labrador Sea and one in the Erminger Sea, and then looking at mixed layer properties, you can see that there's a consistent mixed layer deepening in the winter in the Labrador Sea. There was a really deep mixed layer for this float in the Erminger Sea, but then kind of a more typical shallower mixed layer in 2018. Oxygen here peaks, and total alkalinity also peaks as this mixed layer deepens, whereas there's less kind of notable peaking of oxygen and alkalinity in the mixed layers in the Erminger Sea. So I think that this kind of peaking of alkalinity in the Labrador Sea that we're not seeing, at least for this float, in the Erminger Sea, has some gives some credence to this idea. So kind of where I'm at now is I need to look at more data and understand how get a more full picture of how the alkalinity in the Labrador Gyre compares to that in the Erminger Gyre, and then how this affects the sea surface PCO2, and then sort of thinking about how the whether the alkalinity in this surface layer is elevated due to this sort of export of Arctic water off the shelf, or and mixed layer deepening, and then thinking about how does Arctic water escape off the shelf and into the gyres. And this is all kind of leading to the kind of overarching picture of how does this region act as a carbon sink? Is water that is taking up carbon in the Labrador Sea being evicted to the Oceanography Sea and just releasing that carbon dioxide, or does some of that carbon dioxide actually get, how much of it actually gets exported to depth and stored long term? So that is what I have. Sorry again about the sound. Happy to take any questions. Looks like Izzy has one.
Yes, that was very nice, Monica. Isabella, you have a question? Please go ahead.
Yeah, that was excellent. Really interesting, Monica. Thanks for sharing. I want to make sure first that I understand what's going on, which is another way to think about this is that Atlantic water, like the warmer and saltier it is, it tends to outgas more.
Well, kind of, except that when you look at the maps, like the initial maps right at the start, you don't really like it's not really just the Atlantic water, because it's kind of more in that Oceanography Sea basin, and you're not seeing it in this sort of in the where the North Atlantic current is traveling up. So there's but
okay,
potentially there's like, okay, once it gets somewhat cold enough and getting some deep convection, there's outgassing happening in the Oceanography Sea, and by the time it gets to the Labrador Sea, it's done with that. I'm not really sure.
Yeah. And maybe you said this already, but from these maps, can you tell what it is in the calculation that's making the difference? Like, is it the saturation?
It looks like, yeah. So you can just plot time series at any grid point, and it definitely looks like it's the difference is in this sea surface PCO2. So that's kind of where I've been focusing, looking for something to attribute it to.
Great, thank you.
Any other questions from Monica? I do have a question. What about, you said the difference between the pressure between the sea surface and the atmosphere, right? Have you looked at the atmospheric circulation over the Arctic Sea, if there's anything special about it in terms?
No, I haven't. You mean in terms of like in terms of
I mean in terms of circulation and what defines the pressure of the partial pressure of CO2 in the atmosphere. Have you looked at the atmosphere component?
Yeah, I mean, you can look at the atmospheric. The atmospheric PCO2 is virtually the same over the Oceanography Sea and over the Labrador Sea. But there is that component of wind where the gas transfer velocity, which defines kind of the rate at which the gas is exchanged between the sea and the atmosphere, is governed by wind. And so I haven't looked into the winds that much, but that gas transfer velocity is affected by wind. So that's another potential thing to look into.
Ooh, thank you.
Although it seems like the sea surface PCO2 is more important.
Oh, okay. Thanks.